Let us now find out the center of mass of a uniform solid cone. See, we are given with a cone of mass m and base radius r with an altitude h. Again, as being a solid body, we need to consider an elemental mass, using which we find the center of mass on y-axis. As due to symmetry, we can state that the center of mass of this cone must lie somewhere on its altitude. Again, we consider like a hollow cone a reference point at the vertex, and at a depth y, we consider a disk of width dy. Now, if we consider a disk of width dy, say if its radius is r, we can easily find out its mass. Here, the mass of this disk dm can be given as total mass upon the volume of this cone in which the mass is distributed, that is 1 by 3 pi r square h multiplied by the volume occupied by this disk. The radius of this disk is small r, so its surface area will be pi r square and the width dy, so I'll write pi r square dy. In this situation, the radius of this disk can be calculated simply by the similarity of these triangles, one smaller and other larger. So here I can write r by y is equals to capital R by h. Here you can see this r upon y is equals to capital R upon h. So here this will give us the value of this r. So we substitute, we'll get the value of dm, which is 3m by pi r square h multiplied by pi. Radius can be written as ry upon h whole square into dy. Here pi gets cancelled out. Here you can see this r square also gets cancelled out. We get the value of dm as 3my square upon h cube into dy. This is the value of the mass of this elemental disk. So we can start. We consider an elemental disk of mass dm, where dm is given by this, and y coordinate of center of mass with respect to the reference point can be given by the expression 1 by m integration of dmy. We substitute it, we'll get 1 by m integration of 3my square upon h cube into dy multiplied by y. If we need to integrate y for the complete volume of this cone, the limits of y will be substituted from 0 to h. This will be integrated from 0 to h, so that all such elemental disks are placed one after another and a complete cone is formed. In this situation, this m gets cancelled out. You can take this 3 by h cube out of the sign of integration, and inside it will be y cube dy from 0 to h. We know well that the integration of y cube is y4 by 4. So it is 3 by h cube into y4 by 4. Limits will be from 0 to h. This will be 3 upon h cube into, when we substitute the limits, it is h4 by 4. This h cube gets cancelled out. The result will be 3h by 4. So for the case of a solid cone, the center of mass is located at a depth 3h by 4 below its vertex, and say we are required to find the height of center of mass above the base, so it can be written as h by 4. So keep these two results in your mind. In case of a solid cone, center of mass is at a distance h by 4 from the base of cone and 3h by 4 from the vertex.